Hello everyone, my name is Eric Salas and thank you for joining me in this presentation today. Today I will present the results of our 3-year project that started in July 2013 and ended in November 2016. The one you see below the slide is the full report which was submitted to the South Central Climate Science Center. I would like to recognize first these 3 people who have helped a lot in the project. When I took over the project as the lead scientist, the project was already in its last phase. Before me was Dr. Virginia Seamster, I call her Jeannie. She was the lead scientist of this project and she did all the contacting, the collaborating with our partners, the collecting of the data sets, and even did preliminary runs of our models. So she was more than amazing, transferring the project from hers to mine and mentoring me in the process. I also would like to acknowledge Dr. Boykin for all the valuable inputs related to the species history and the species information. And lastly, our climatologist, Dr. Keith Dixon from the NOAA Geophysical Fluid Dynamics Lab in Princeton University, for sharing his expertise on anything climate related, most especially in helping us in the selection of our climate models. My presentation would go like this. I will give you a little summary of the project, then a little literature background. I will show you our methods as well as the data sets we used, then the results, and lastly the conclusions and some future plans. We had a threefold objective. We wanted to develop models of present-day and future distributions of suitable environmental conditions for 20 focal species in the south central US. We wanted to compare how bioclimatic envelope suitability is projected to change among the different climatic scenarios. And lastly, we wanted to integrate our results into the New Mexico Crucial Habitat Assessment Tool, or the NMChat, and into the USGS Science-Based Catalog. For our methods, we obtained 19 raster-based bioclimatic variables from among the WorldClim datasets. As you can see in the right side of your screen, these are temperature and precipitation variables varying in temporal scales. So we used them to describe the present environmental conditions and explore the relationships between the bioclimatic conditions and the species distribution patterns. We also used 5 species distribution modeling algorithms, or SDM. So we have the generalized linear model, the random forest, the boosted regression tree, the very popular Maxent, and the multivariate adaptive regression splines. We also used 4 general circulation models, or the 4 climate models. I will explain more later on how we selected these GCMs, as you can see on the slide. And then we use 2 climate scenarios, or RCPs. These are also known as the greenhouse gas emission scenarios. We use the RCP 2.6 and the RCP 8.5. The RCP 2.6 is the most aggressive of all the scenarios, and the RCP 8.5 is the most extreme of all the scenarios. So the RCP 2.6 assumes that the global annual greenhouse gas emission would peak between the years 2010 to 2020, while the RCP 8.5 assumes that the greenhouse gas emissions would continue to rise throughout the 21st century. And finally, we used 2 time periods. That means we projected the present condition of the species to 2 future years. We selected the year 2020, 2050, and the year 2070. We hypothesized that the current suitable bioclimatic conditions of our focal species would become unsuitable conditions in the future. And with these unsuitable conditions, focal species would be at higher risk due to climate change. Speaking of climate change, here is a map from the climatewizard.org. So this is a project by the University of Washington, University of Southern Mississippi, and the Nature Conservancy. This shows us the mean temperature difference or the map of temperature change by the year 2080 relative to the year 1970. So this is a product of an ensemble averaging 16 climate models. So the map tells us that there would be an increased average annual temperatures of greater than 5 degrees Fahrenheit by the year 2080. And this increased average annual temperature would lead to increased occurrence of extreme climatic events such as drought and heat waves, as well as increased occurrence of large fires. So how will climate change affect species? First, it modifies the species habitats. Next, it leads to the shifting and the contracting of the species distribution. That means it changes the species range and distributions. Third, it influences disease dynamics and it could trigger the outbreaks of diseases. Although we believe that some species could adapt to the climatic changes because of their ability to disperse and maybe move somewhere else, there are species like, for instance, the reptiles and the amphibians that may not be able or mobile enough to move or to adapt to the local climate stresses, and eventually they just go extinct. These are the three factors we use to assess species vulnerability to climate change. If the species is exposed to climate change, if the species is sensitive to climate change, and what the probability of the species to adapt to climate change. The areas of overlap correspond to the different potential outcomes for the species. For example, species in the middle, which are exposed, sensitive, and have low adaptive capacity to climate change, these species could experience extinction. But most importantly, these are the species of greatest concern. So these species must be the first priority for monitoring responses to climate change, as well as for assessing the interventions needed to support these species. Those in group 2 are what we call potential adapters. So they are sensitive and exposed to climate change, however they have high adaptive capacity to the change of the climate. So these species may be able to mitigate the negative impacts of climate change through dispersal or maybe through microevolution. Those species in group 3 are what we call potential persisters. So they have low adaptive capacity and are exposed to climate change, however they are not sensitive to the change of climate. So these species may be able to withstand the change of the climate in their own environment by themselves. And finally, group 4 species are what we call high latent risk species. So they have low adaptive capacity and are sensitive to the climate change, however they are not exposed to climate change. So these species may be safe for now, however they could still be potentially vulnerable in the future. Here is a quick overview of how species distribution models work. So from this diagram over here, let me just quickly open my pen. So for SDM to work, you need to have a data set consisting of your species occurrence or the species geographic locations. You need to link this data set to another set of data, which is the species environmental data set. And to link, you need to have a statistical framework or some kind of a modeling framework to produce the map of predicted occurrence of the species. So the species could be, or the product could be the current condition of the species if you are modeling its present condition. We recommend that when you model, you have to use part of your data for calibration and part of the data for validation. So what you can do next is to project the current condition of the species to some future years to see how the species condition or the species habitat would look like in some future years. Our research employed a 4-step methodology. The first step is the inputs, which includes the species occurrence, the species ranges, as well as the bioclimatic variables. We use these data sets to model the current conditions of the species, which is step 2. This step also includes the selection of the different SDMs as well as the generation of the current conditions of the species. Once we had the current condition of the species, we then projected it to the future condition, and this step also includes the selection of the different climate models as well as the selection of the RCPs. Once we had the future condition of the species, we compared it to its current condition in step 2 to produce the projected bioclimatic envelope of the species. Our results were then integrated to the ICLUS, which I will discuss later in the presentation, and integrated into the chat or the New Mexico chat tool. We spent sufficient time in selecting the species we need to model out. As you can see in the diagram, we started with 246 species listed on the species of concern layer for the New Mexico chat. We looked at the different characteristics of the 246 species, and we used these characteristics as filters. And then we trimmed down the number of species from 246 to a much smaller number. In our filters, we asked if the species are of greatest conservation need in New Mexico or Oklahoma and Texas. Is there any evidence of the species' vulnerability to climate change? And most importantly, we asked for feedback from the stakeholders. It took us many weeks to finally get to a final list of 20 species, from amphibians to birds to mammals to reptiles. I want to point out that some of the species are not only species of greatest conservation need in New Mexico, but as well as in some other states. For example, there are birds and mammal species that are species of greatest conservation need in 3 states. Here are the selected 20 species of greatest conservation need. 3 amphibians, 9 birds, 6 mammals, and 2 reptiles. I want to highlight that the 2 birds with red dots are actually birds that are species of greatest conservation need in Oklahoma and Texas, but not in New Mexico. The diagrams here show the 20 species ranges from the USGS GAP. You see that some species are endemic species, such as the Jemez Mountains salamander, and some species are more widely distributed compared to the others. Some have fairly well distributed occurrence points, as you can see in the figure on your right. We use this species range dataset as a boundary layer in modeling its species because we wanted really to limit the extent of where we could project the future conditions of the species. The choice of the extent of the species range was very critical in the performance of our models. We believe that selecting a range that is too broad or too restricted could negatively affect the relationship between background and presence points in our models. Our datasets came from these sources online: the Bison, the HerpNet, the ORNIS, and the VertNet, as well as from the natural heritage programs of New Mexico, Oklahoma, and Texas. We combined all these datasets from the different sources to a coherent dataset for each species, and we limited the datasets to the period of our climate data and to the spatial extent of the USGS species range. This is how we selected our climate models. We started with 17 GCMs. These GCMs were studied by Maloney et al. 2014, and these models could be applicable to the continental US. You see the 17 GCMs in the table on the right of your screen. These models are models generated by laboratories around the world, and they differ from one another because they use different sets of equations to capture the atmospheric dynamics. What we did was we performed a qualitative assessment of how well these 17 models would capture the climate in the study area in the south central region of the United States, based on the quantitative assessment performed by the authors Forster et al. And Sheffield et al. 2013. The criteria we utilized in selecting the GCMs were 3. The first one, there should be a smaller differences in model output relative to historical data. That means we measured the bias and we wanted to have a small bias. Second, the model should have a minimal or no energy budget imbalance. Energy imbalance has something to do with the energy budget of the model. There is an issue that if the model is out of balance, then it can become warmer or colder over time just by itself without any forcing. Thus, we need to take into account for this drift when analyzing the magnitude of the impact of the forced scenarios in the global climate. Otherwise, we may over or underestimate the effects of the different greenhouse gas emission scenarios. And the last one, we looked at the availability of the downscale data for the GCM. So if there is no available data for that GCM, we took it out from the list. After the extensive assessment, only 4 passed our criteria. So I think 4 is a very good number of models to analyze. So we want to point out that these 4 are not the best, nor are those unselected models inferior. So these 4 models just happen to perform well based on how we evaluated them for the region of interest, that is in the south central region of the US, and how they were able to really capture the variations of the climatic variables important for our 20 species. We also would want to highlight that these 4 models may not be the best models for all related studies. Our goal in selecting the GCMs was to see whether the combination of climate models and greenhouse scenarios could capture a good range in potential future conditions. These diagrams here showed our selected 4 models and how they plot against each other in terms of the key climatic variables important for our selected species. For example, let me open my pen. The figure on your left shows HE projecting a much warmer climate in drier months, while C is projecting a much colder climate in wetter months under both RCP 8.5. And for RCP 2.6, HE is projecting a much warmer climate in wetter months, while C is projecting a much colder climate in wetter months. In the end, we wanted to look at a range of futures, not look at multiple futures that are all of the same climates. For our analysis tools, we use the VStrails software for assisted habitat modeling. So this tool allows us to compare 5 statistical algorithms: the maxent, the boosted regression tree, random forest, generalized linear model, and the multivariate adaptive regression splines. We also used R and the packages of R, and lastly the Python and ArcGIS. For our results, again we had 20 species, used 5 SDMs, 4 GCMs, and 2 time periods, and that gave us 80 models per species, or 1600 models for the 20 species. But since we could not actually present all the 1600 maps or models, we did an ensemble, and in the end we came up with 4 models per species. That is a combination of the RCP 2.6 for the year 2050, RCP 2.6 for the year 2070, RCP 8.5 for the projected year 2050, and RCP 8.5 for the projected year 2070. So a total of 80 models for future scenarios for the 20 species. We want to take note that we also run the RCP 4.5, and we did have results for the RCP 0.5, and that would give us a total of about 2400 models all in all. However, as I've said in the beginning of the presentation, that we didn't present or submitted the results for the RCP 4.5, as we only presented results for RCP 2.6 and RCP 8.5. Here are the results for the quails. The green color means that areas that are currently suitable for the species remain suitable in the future. The yellow color means that there are new suitable areas that are projected in other locations in the future. The red color means loss of the present suitable envelopes for the species. And last, the gray color means that the areas are unsuitable for the species in the present and in the future. Let me just get my pen quickly. The first column here shows you the current condition of the species. The second column shows you the projection to the year 2050, and the third column shows you the projection of the suitable habitat for the species in the year 2070. So this set right here is for the RCP 2.6, while the set over here is for the projection using RCP 8.5. Among the quails, I want to highlight the white-tailed ptarmigan, because the white-tailed ptarmigan would lose 62% of its suitable bioclimatic habitat by the year 2050, and 67% of its bioclimatic habitat would be lost by the year 2070. Here are the numbers quantifying the gains and losses of the species' suitable climatic envelopes. So while there seems to be increases seen for the scaled quail and the northern bobwhite quail, there is a different story that is happening for the Montezoma and the white-tailed ptarmigan. On average, around 62% of the suitable climatic envelopes will be gone for the Montezuma quail and 76% for the white-tailed ptarmigan. In general, there are more losses than gains for the quails in almost all the scenarios. And most importantly, among all the 9 birds we modeled, the quails are the ones that would be most affected by climate change. Here are the results for the rest of the bird species. You see more yellows and greens for the cousin sparrow, and in contrast, let me get my pen again. Here's the cousin sparrow, and in contrast you see more reds or losses for the lesser prairie chicken. And here are all the reds for RCP 2.6, and you see so many reds here for the RCP 8.5. Now, of all the bird species that we modeled, it's only the cousin sparrow that has more than 50% gain in total area of suitable bioclimatic conditions for all the future climatic scenarios we did or we run. And you can see this from all the yellows that you see in the RCP 8.5 map. Here is a look at the numbers for the cousin sparrow as well as for the lesser prairie chicken. An average of 71% gains for the cousin sparrow was observed, while there is less gain for the lesser prairie chicken and more loss. So the lesser prairie chicken would lose an average of 63% of its bioclimatic envelope suitability with very minimal gains. However, we did find a large area in northwestern Kansas which we identified as currently containing suitable climatic conditions for the lesser prairie chicken. The area is part of the short grass prairie, which is a type of environment associated with the lesser prairie chicken. And this result is actually the same as the one that's found by Jarnevitz 2016 that showed a high rating of suitability in the same northwestern region of Kansas. Here are the projections for the 6 mammals. 3 mammals showed more gains than losses for the suitable bioclimatic conditions in all of the projected scenarios. They are the black-tailed prairie dog, this swift fox, and the Gunnison prairie dog. In these graphs, you see the positive numbers for the black-tailed prairie dog, the swift fox, and the Gunnison prairie dog. And contrast that to the numbers for the northern pygmy mouse, where you see an average loss of 82% with very minimal gains. These are the future projections for the herpetofauna, the reptiles and the amphibians. While you see the Hemes mountain salamander to be covered with mostly green, that's the center row, there is a large percentage decrease in area is observed for the western river cooter, which is the last row, and the gray checkered whiptail, which is the second to the last row, for all of the climate scenarios. Here are the numbers for the decreases in areas I mentioned for the western river cooter and the gray checkered whiptail. The gray checkered whiptail would lose all of its current suitable envelopes, while the western river cooter would lose about 86% of its present suitable conditions, with minimal to no gains in the future. The Hemes mountain salamander is the only herpetofauna species that had a less than 1% loss, making it the only species that may not be at risk for climate change, since its current distribution would not be affected significantly. This minimal loss of the Hemes mountain salamander may have something to do with the size of the species range. We did check the projected areas of the Hemes mountain salamander, and those areas are on elevations between 2130 and 3435 meters, which are elevations that fit the species requirement of high elevation areas. And also, the most important climatic predictor for the Hemes mountain salamander was the mean temperature of the coldest quarter, and this also fits the low critical thermal maximum characteristic of the species, meaning that the Hemes mountain salamander can adapt to the low temperature in higher elevations. We integrated our projections to the data from the ICLUS or the ICLUS. It's the Integrated Climate and Land Use Scenarios. So the ICLUS project was under the EPA, or the Environmental Protection Agency. So it explores the future changes in population, human population, the housing density, and the impervious surface for the United States. The only downside of the ICLUS is that it utilizes the Special Report on Emission Scenarios, or the SRES, that's the old one, and not the new one, which is the RCP. These are scenarios for greenhouse gases. Therefore, we were limited to the datasets that we could use and compare. In the end, we used the impervious surface projected to the year 2050 and 2070, both under the ICLUS A1 scenario. So this matched our projections to the years 2050 and 2070 under the RCP 8.5. This is a sample map of what we found. We divided the ICLUS impervious surface into percentages. For example, the percent IS3 are pixels, ICLUS pixels covered by 20% to 35% impervious surface. Percent IS4 are pixels that are covered by 36% to 60% impervious surface, and percent IS5 are pixels covered by 61% to 100% impervious surface. When we integrated our 2070 projections for the northern bobwhite quail to the ICLUS, we found that those ICLUS pixels covered by 61% to 100% impervious surface in 2070, that's coded percent IS5, would never affect the projected future suitable envelopes we have modeled for the species. ICLUS pixels that covered by 36% to 60% impervious surface in 2070, or IS4, will only affect about 0.4% of the projected future suitable envelopes of the northern bobwhite quail, and that is actually very minimal, knowing for the fact that the northern bobwhite quail has the largest range among all the 20 species in the study. We concluded that in both years 2050 and 2070, majority of the stable area projected for the 20 species would only be minimally affected by the projected impervious surface in the United States. In fact, in all of the 20 species, the effects of the impervious surface could only be seen in the IS1, which are pixels that are covered by 0% to 5% impervious surface. And finally, no species would lose its stable bioclimatic envelope due to the increasing impervious surface cover in the United States. For the final step of this research, we incorporated our results to the state-level chat. So we integrated our projected future scenarios into a decision support system, or a DSS, using the statewide New Mexico Crucial Habitat Assessment Tool, or the NM chat. You can check how the chat looks like by visiting the link provided. And what is a chat? Chat is a summary DSS that's used for identifying crucial habitat for wildlife species. Let me show you what we did in the chat. This gray shape is the layout of the state of New Mexico. Zooming in, you see that in the chat tool, New Mexico is divided into 1 square mile resolution hexagon grid. If you count all hexagons in New Mexico, the total is 123,000 hexagons. Each hexagon has a corresponding ID, as you can see in the table. We looked at the classification of the 20 species, whether it's gain, loss, stable, or absent for each hexagon. We placed 0 if the species for that hexagon is absent, 1 if the species was lost in a particular projection year for that hexagon, 2 if the species has gained suitable envelopes for that hexagon, and 3 if the species is stable for that hexagon. With the power of coding, we did this for all of the 123,000 hexagons. And finally, each hexagon was scored with respect to the number of species lost in the year 2050 and in the year 2070 relative to the current day count of the species against each climate change scenario. This is a sample result of the chat integration that you will see online. We named it as Relative Diversity Loss Index, or RDLI. RDLI provides a summary index representing the relative percentage loss of species diversity across the state of New Mexico for each climate scenario and time step at a 1 square mile scale. To interpret the RDLI, just please refer to the image. The red on the map shows that there are more number of species lost in those regions of New Mexico in the year 2070 using RCP 2.6 compared to the green areas with less number of species lost. A summary of the map is reflected in the bar graph, where you see that around about 20,000 hexagons having greater than 75% of the species lost. RDLI is relatively simple and intuitive, and you can visit the link nmchat.org to query the underlying species content for more in-depth analysis. And we recommend that you will use this RDLI in conjunction with other layers of the chat to provide a more contextual framework for developing a response to climate change. We hope that we could explore and learn more how practitioners would respond to the availability of RDLI online, which really tells the effects of future climate change for wildlife in New Mexico. And we also hope that our results would be integrated to the other chats in some other states, like for instance Texas and Oklahoma. In conclusion, this study looked only at the effects of climate to the species. However, we think that the bioclimatic variables alone may not always correctly identify current or future suitable conditions for the focal species. It would be better if species-specific non-climatic variables should be used to eliminate questionable model locations. Our study used a low spatial resolution for the climatic variables. That means our results did not capture microclimate nor other local environmental conditions or characteristics such as stream temperature or soil moisture. We think that the Sacramento Mountain salamander and the Jemez Mountain salamander may persist in their mountaintop habitats if microclimatic conditions provide sufficient moisture. Our study restricted the species range. So in the future, we would like to extend this species range so that we could accommodate species that are mobile. And given what is known about the current distribution and the habitat preferences of the species, there's still a question that remains whether the species populations would exist in those areas we projected in the future outside the species range. So the question is, would it be possible for this species to move in those new areas without assisted migration? This project has resulted into a number of peer-reviewed publications. The first one is the final report that we submitted to the Climate Science Center. We have one paper specifically for the birds that is now available online. So this paper, we did a little modification on the ranges of the species or the birds to take into account the species mobility. And you can find this one in the link provided in here. The next paper was focused on the whiptails, and it is now available via the journal Climate. This paper uses the RCP 4.5 and the RCP 8.5 instead of the RCP 2.6 and the RCP 8.5 that we used for the report. We also have a paper that is now ready for publication on the Herpetological Conservation and Biology journal, and this will come out soon online. And lastly, all results and maps that we produced for this project can be downloaded for free through the USGS Science Base website. We acknowledge the USGS for the funding via the South Central Climate Science Center. We also would like to thank all the stakeholders from organizations in the South Central region for the help and the inputs on the species selection process. And the rest of the people involved in this project, thank you so much. If you have questions about the results or our datasets, please email me here. Here's my contact, and I'll be glad to help you. And thank you so much for joining me in this presentation.